Let's look at some properties of Jacobians. Let's say u is a function of s and t. V is also a function of s and t. Now this s and t, s itself is a function of x and y, and t is a function of x and y. So if that is the case, then dou u comma v with respect to s and t multiplied by dou s comma t with respect to dou x comma y is equal to dou u comma v with respect to dou x comma y. It's as if this and this are being cancelled. Okay, so let's see whether we can prove this or not. And as usual, we take one of the sides. So let's take the left hand side and let's take each term. So dou u comma v by dou s comma t is equal to, remember this is a determinant, us ut, right? Dou u by dou s, dou u by dou t, dou v by dou s, and dou v by dou t. And similarly, dou s comma t with respect to dou x comma y is equal to, again a determinant, dou s by dou x, dou s by dou y, dou t by dou x, dou t by dou y. Now let's multiply these two. Dou u v with respect to s t times dou s t with respect to x comma y is equal to, now we have to multiply these two matrices, and you should remember the rules for multiplying. So dou u by dou s times dou s by dou x plus dou u by dou t times dou t by dou x, then dou u by dou s times dou s by dou y plus dou u by dou t times dou t by dou y. Similarly, let's take this now. Dou v by dou s times dou s by dou x plus dou v by dou s times dou v by dou t, dou v by dou s by dou x, dou v by dou t times dou t by dou x, dou v by dou s times dou s by dou y plus dou v by dou t times dou t by dou y. Okay, now remember u and v are functions of x and y, so which means let's take it one by one. Dou u by dou s times dou s by dou x plus dou u by dou t times dou t by dou x. This is equal to what? Now think carefully. Here a small change in x leads to a change in t. A small change in t leads to a change in u. Small change in x leads to a change in s. Small change in s leads to a change in u. So basically, small changes in x leads to a change in u via s and t. Yes. So this is nothing but dou u by dou x. Let's look at the other one. Dou u by dou s times dou s by dou y plus dou u by dou t times dou t by dou y. Now again think carefully. A small change in y leads to a change in t, and a change in t leads to change in u. Similarly, a change in leads to a change in s, and that change in s leads to a change in u. So basically, a small change in y leads to a change in u via changes in s and t. And when you sum it up, basically what you get is dou u by dou y. Now let's look at dou v by dou s by dou x plus dou v by dou t by dou x. So a change in x leads to a change in v via s and t. So dou v by dou x. Okay, dou v by dou s by dou y plus dou v by dou t times dou t by dou y. A change in y leads to a change in v via changes in s and t. So dou v by dou y. So which means our matrix becomes, this is dou u by dou x. Yes, this is dou u by dou y, dou v by dou x, and dou v by dou y. And this is nothing but change in u and v with respect to x and y, which is what we had to prove. Okay, now let's look at the second property. If u is equal to, so u is a function of x and y, and v is a function of, again, x and y, then dou u with respect to dou x comma y and dou x comma y with respect to u and v is equal to 1. Okay, now let's see what how to prove this. Now remember, u and v are independent functions of independent variables and vice versa. So which implies that dou u by dou v is equal to 0. So any change in v doesn't lead to a change in u. Dou v by dou u, so a change in u doesn't lead to a change in v. Dou u by dou u is equal to 1. Dou v by dou v is equal to 1. Again, as usual, let's take the left hand side, dou u, dou v. Let's do it separately, one by one. Dou u comma v by dou x comma y, okay, LHS, times dou x comma y by dou u comma v is equal to, remember again, the determinants. So this would be what? Dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y multiplied by dou x by dou u, dou y, no, dou x by dou v, dou y by dou u, dou y by dou v. Let's multiply them. Let's make some space for ourselves. Dou u by dou x times dou x by dou u plus dou u by dou y times dou y by dou u. Dou u by dou x times dou x by dou v plus dou u by dou y times dou y by dou v. In the same way, dou v by dou x times dou x by dou u plus dou v by dou y times dou y by dou u, dou v by dou x times dou x by dou v, dou v by dou y times dou y by dou v. Okay, a change in u leads to a change in y, and that change in y leads to a change in u. Okay, so you got the idea. This would be dou u by dou u. Similarly here, a change in v leads to change in y, change in y leads to a change in u. That same change in v leads to a change in x, which in turn leads to a change in u. So dou u by dou v, and finally dou v by dou v. Now here we have already evaluated this, so this would be dou u by dou v would be 1 0 0 1, which is nothing but 1. Okay, so that's the second property. Let's look at the next property. So let's say u is a function of x, y, and z. V is a function of x, y, and z, and w is a function of x, y, and z. Now, if these functions are functionally dependent, if these functions are functionally dependent, then in that case dou u v w with respect to dou x, y, and z is equal to 0. So basically what we mean by functionally dependent is that these functions can be written as u v w equal to 0. Now this gives us, so let's look at this equation. This basically implies that dou p by dou u by dou x plus dou p by dou v by dou x plus dou p by dou w times dou w by dou x is equal to 0. Okay, then dou p by dou u by dou y. Again, remember, you have to think of it step by step. A change in x, change in w, change in p. A change in x leads to a change in u v w, which in turn leads to a change in p. So when you sum up these, get 0 because they are functionally dependent. That is why the total would be 0. Okay, plus dou p by dou v times dou v by dou y, dou p by dou w times dou w by dou y. Okay, is again 0. Dou p by dou u by dou z plus dou p by dou v times dou v by dou z plus dou p by dou w times dou w by dou z. Now this is where you have to be careful. See, what happens in higher mathematics is many steps are skipped, assuming that the student knows. So if you write the determinant of this, what you would end up with is, now remember, based on the properties of determinants, we can take out commonalities, right, within a column or within a row. Now if you look at these columns, in each of the first column elements, dou p by dou u is common, right? So which means dou p by dou u can be taken out. Similarly, from the second column, dou p by dou v can be taken out. And from the third column, dou p by dou w can be taken out. So we are left with what? Now, these three will get cancelled out. Why? Because if you take it to the other side, it becomes 0. So we are left with only the determinant. Yes. And this basically determinant. So let me just cancel it off. But remember, this will go to the other side, and because it is 0 divided by that, it will become 0. So now if you look at this determinant carefully, what is happening is the rows contain the similar denominators. Yes, dou x, dou x, dou x, dou y, dou y. So these are the rows. What we want is the same thing in columns. Okay, so we want du by dx, dv by dx, dw by dx as a column. Again, you have to remember that when we talk of determinants, the transpose of a determinant doesn't affect the determinant. And again, if you notice carefully, this is nothing but u, v, w with respect to x, y, and z. So that proves this third property, that if u, v, and w are functionally dependent, then their Jacobian is equal to 0. Okay, in the next session we'll look at some problem solving based on these properties. I think enough for today. Bye for now.